Right now, a team of astronomers is running an active scan across millions of stars, hunting for an incredibly specific heat signature. Through an initiative called Project Hephaestus, they are looking for the thermal exhaust of alien megastructures. The logic here relies on the Copernican principle, the idea that humanity isn't uniquely special. We are already taking our first steps into off-world manufacturing and space solar power. If that natural progression holds true across the cosmos, older extraterrestrial civilizations should have mastered stellar engineering millions of years ago. But here is the actual problem. When we look out into the vastness of the galaxy, we see absolutely nothing. If highly intelligent life inevitably builds massive structures to harvest starlight, our universe should be glowing with their infrared footprints. Instead, it is completely silent. Finding one of these structures proves that advanced life exists. But failing to find them points to a much darker possibility, that perhaps civilizations struggle to survive the sheer scale of their own technological ambition. To reach the next stage of planetary evolution, what physicists call a Kardashev Type 2 civilization, a species must learn to harvest the entire energy output of its host star. Pop culture pictures a Dyson sphere, a solid shell enclosing a sun. But physics dictates a solid shell is gravitationally unstable. Mechanical stress would cause it to crumble inward. The viable blueprint is a Dyson swarm, millions of independent orbiting solar collectors, collectively beaming power. Because orbital mechanics dictate that a swarm is the only workable way to harvest a star, we know exactly what physical mechanics to look for in the night sky. We just need to understand how the system actually functions. Capturing the sun's energy is only half the equation. The real logistical hurdle is transmission. Once your millions of satellites have trapped all that stellar radiation, how exactly do you send that power across millions of miles of empty vacuum back to your home planet? Science fiction writers solved this on paper long before we had the engineering to test it. Isaac Asimov conceptualized wireless energy transfer in space decades ago in his short story Reason. Today, that concept is leaving the realm of fiction. In the Caltech Maple experiment, engineers are testing this process in orbit. A solar satellite collects sunlight, converts it to direct current, and transforms it into a radio frequency microwave. Using phased arrays, the satellite focuses and beams those microwaves to a destination on Earth, converting it back into usable electricity. Microwaves aren't the only option. Lasers can also push energy across space. The Breakthrough Starshot project, initiated by Yuri Milner, has proposed using a massive 100 gigawatt phased laser array to beam power directly at light-sail spacecraft. Space solar power and targeted energy beaming are physically proven mechanisms. Human engineers are building the prototypes right now. So if the mechanics work, the complete lack of alien swarms suggests that turning a star into a battery comes with a catastrophic hidden cost. That hidden cost is the habitability dilemma. Pumping an entire star's worth of captured energy back into a closed planetary biosphere has an inescapable thermodynamic consequence: massive waste heat. Modeling shows beaming a full Dyson swarm's energy raises Earth's temperature by 140 Kelvin, a lethal boiling event. A 4% partial swarm still causes a 3 Kelvin increase. Swarms between Earth and Sun induce global cooling, while external ones reflect radiation, baking the night side. Generating infinite power creates a direct physical threat to the environment consuming it. Operating a massive stellar swarm puts the very planet you are trying to power at constant risk of thermal collapse. This thermodynamic trap completely reframes the Fermi paradox. When we look at the silent, empty universe, we might not be looking at a lack of intelligent life. We might be looking at the victims of the habitability dilemma. Stellar engineering requires pushing a civilization's energy consumption to its absolute physical limits. Attempting to wield that much power without frying your own biosphere may act as a universal great filter, a test that destroys the vast majority of species that try it. For an advanced civilization to actually survive this transition, they must calculate an incredibly precise balance. They have to optimize their swarm configurations to harvest enough energy to thrive, while maintaining a rigorous, flawless stewardship over their planet's climate stability. We already know how to beam power through a vacuum, and we are already designing the technology to harvest the sun. The ultimate test for humanity won't be whether we have the engineering genius to build a megastructure. It will be whether we have the wisdom to survive operating one.